Yes, I've done 2 mass oscillator, coupled oscillator, but we haven't done 3. So let's do 3. So this is going to be 3 masses connected by springs, and we're going to find the normal mode. So we need a quick review. Let's think about what happened with the 2 mass oscillator, because we're going to do the same thing. I'll post a link to that video for the full details below. But if I have 2 masses connected by springs, so there's spring, 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 mass, mass, different spring constants, different masses, all that stuff, I can write the following 2 equations of motion for x1 and x2, the positions of the 2 masses. So if I just do a little bit of algebra, it's not a big deal. I can get it in this form where something times x1 plus something times x2, something times x1, something times x2. If I assume a solution such that both x1 and x2 have the same angular frequency, omega, then I can write the solution as a vector for both x1 and x2. So I'm going to say they have a constant a1, a2 times that solution, and I want to find these constants a1 and a2 for normal modes. That's only for normal modes, right? Because they have the same angular frequency. And their uniform frequency. And then you can take the second derivative, you get a negative omega squared in front of there, and then I can write this as a matrix times the vector x, and this exponential stuff cancels. I'm going through this so fast, okay, because I want to do the 3 mass thing. And so you get to this. So this is the, and I divide by m right there, I divide by negative, and I get these terms. So that's my acceleration, the exponential canceled, omega squared comes from that. There's my matrix, and there's my other vector. So this is the eigenvalue problem because I have a matrix times a vector, and I get back the same vector with a scalar in front of it. And so how do you solve that eigenvalue problem? Well, then you have to take a determinant. No one wants to do that. We'll do that in Python, but setting it up the problem is the most important thing. Okay, let me jump over to Python real quick and show you what this looks like. So this is not a normal mode, but I did create this. Here is, make this big. That's good. Here is 3 masses. All I did was move mass 1 a little bit to the right and let it go, so then it can do everything. And I think I have spring constant here and there are stronger, and these are weaker. And then all the masses are the same. So let's just run this and see what happens. This is not a normal mode. It's not a normal mode because they're not moving the same frequency. The graph shows that too, right? Down here, they don't have constant motion, constant trig motion, and all that stuff. So what we want to do is to find those initial values for the initial positions of the masses. So then when I let it go, boom, normal mode. And so this is our testing platform, and I will give you a link to this code so you can test it. But, I mean, there's nothing magic here. Let me just show you really quickly. So I make all the objects. There's a bunch of just objects there, right? Masses, M1, M2, M3, K1, K2, K3, K4, L. Oh, L is just a spacing. So I have these 2 masses, these 2 points on the end, and I want to put the masses evenly spaced. Then I have their initial positions. S is just what I'm calling it. Initial velocity. And then there's my cars, my springs. And then here, all I'm doing is calculating the force. Each mass would have 2 forces acting on it because of the 2 springs. Once I know the force, I can divide by the mass and get the acceleration. Once I know the acceleration, I can use that to update the velocity. Once I have the velocity, update that to get the position. Use that to update the position. And that's it. And then I just move all the visual objects and stuff and make a graph. Okay, so it's not that big of a deal. It's kind of a big deal, but not really. Okay, so let's go back to the 3 masses. That was really quick. So here are my 3 masses. I'm going to do the generic case. So I have the 3 masses. Mass 1. Mass 2. And you have to say them when you draw them. If you don't say mass 1, mass 2, and mass 3, it's like they don't exist in the world. And just to make things as easy as possible, we define the position of mass 1 as measured from here, x1, the position of mass 2 measured from here, x2, the position for mass here, x3, and this is going to be k1, k2, k3, k4. Okay, so I want to go ahead and write down the equation of motion for mass 1. So I can write m1 x1 double dot. That's the mass times acceleration, and that's going to be equal to the net force. Okay, it's not too bad because each mass only has 2 springs. So right here, I know if I pull it this way, I'm going to get a negative force from that one. So let's write negative k1 x1. Now here, we did the same trick before. If I move it this way, then this spring's going to get compressed and push it back. So I'm going to get a negative k2 times x1. But if x2 moves the same amount, then I get no force, right? So this is really just going to be x1 minus x2. Let's just check, right? If that stays stationary and I move it, I get a negative backwards pushing force. If I keep that stationary and move x2, then it should pull it forward. So if x2 is positive and x1 is 0, then I get a positive force. That's good. Now, one of the things I'm going to want to do to get it in the format of the matrix, I want to rewrite this in terms of x1, x2, x3. So let's write that over here as get all the x1s together. So if I have a negative k2 x1, negative k1 x1, I'm going to write this as negative k1 plus k2 x1, and then I just have that 1 x2, so I'm going to say plus k2 x2, and then you can say plus 0 x3 if you want. And so now you can see if I'm getting in the format that I can put it in a matrix. Now let's look at the second mass right here. So m2 x2 doubled. I'm actually going to divide both sides by the mass. That will be important later. m2 x2. Okay, so this one has, if it moves that way, that's going to pull back, but it depends on that one too, right? So this is going to be negative k2 times x2 minus x1. Right, because it's moving this way, it's going to get pulled back unless that one gets pushed forward. Now I have this one, the same thing over here. I'm going to write this as minus this spring, k3, times x2 minus x3. Right, because again, it's the same as that, except I'm doing this spring right here. So that moves forward, it gets pushed back. Now let's write that in terms of x1, x2, and x3. So x1, I have a negative x1, negative k2. That's only x1. So let's write that as k2 x1. Now I have a x2, I have negative k2, I have negative k3. So this is going to be minus k2 plus k3 x2. And then my x3 term, I only have this one right here. Right, that's the only, so it's just going to be plus k3 x3. Now let's do the last mass, m3 x3 double dot. I'm going to get this negative k3 times x3 minus x2. Yeah, that's right. And then I have that one's pretty easy. It's just going to be minus k4 times x3. And again, we're going to separate it out. I have 0 x1. There's no x1s. My x2, I have a positive k3. That's it. Yeah. So plus k3 x3. And then I have no x2. And then I have x3, I have minus k3 plus k4 x3. That's good. Okay, now what I'm going to do to get it in the form of the matrix I want. Remember, when I take that second derivative of the position, I'm going to get a negative sign. So I'm going to go ahead and multiply both sides by a negative sign, and then that will give me the k. I'm going to divide both sides by the masses. I have to divide this stuff by m1, this stuff by m2, and this stuff by m3. And we're going to call this, so let's just write that out. So I'm going to say negative x1 double dot is going to be equal to k2. Let's write it out. Oh, no, I'm sorry. I'm using this right here. Just throw a piece of paper away. So we're going to say negative x1 double dot equals, I'm using this. So I have k1 plus k2 over m1 x1. And then I get minus k2 over m1 x2. And that finally, I'm just get 0, x3. Now for the next one, right here, I have negative x2 double dot. It's going to be equal to negative k2 over m2, right? Because I'm dividing both sides by m2 because there was an m2 there. Plus, oh, that's x1, plus k2 plus k3 x2 over m2, and then I get minus k3 over m2 x3. That's a 3. See that? And then finally, I get this last one, negative x3 double dot is going to be equal to this 0, x1, minus k3 over m3, that's a 3, m3 x2, and then plus k3 plus k4 over m3 x3. So now I can write this as my, we're going to call that my k matrix, right? So I want to get this in the form of negative omega squared x vector equals the k matrix times x. And that's my eigenvalue problem. So this k, that's a capital K. Look, I'm going to put a capital there. It's capital K. So let's write capital K as the matrix. It's just going to be this k1 plus k2 over m1, negative k2 over m1, 0. And then the next term is going to be this, negative k2 over m2, k2 plus k3 over m2, negative k3 over m2. And then finally down here, 0, negative k3 over m3, and then I have k3 plus k4 over m3. So the way you would solve this is you'd multiply both sides by the identity matrix, then you'd subtract this. Actually, I already multiplied by the negative, see? You subtract this omega squared, so you get a minus omega squared, minus omega squared, minus omega squared. Take the determinant of that matrix and set it equal to 0. And there is no one that wants to do that. I'm almost positive that no one wants to do that. So instead what we're going to do is I'm going to enter this matrix in Python, and I'm going to have to use real Python. I can't use web vPython because real Python has NumPy, it has linear algebra, it has the eigenvalue function in there. So I can give it this function, and then it can give me the eigenvalues and the eigenvectors, and that's what I want. Okay, I want the A1, A2, A3 because those are my initial conditions for X1, X2, and X3. Let's put this in and see what happens. Okay, I am switching over here to, I'm using Google Colab. Okay, so Google Colab is like Python. It is Python, but you don't have to install anything, so it's kind of awesome. And if you haven't used this before, there's these cells, and you can run each cell. You can put other stuff in them too, but I'm just going to use it as simple as possible. The first thing I want to do is to import NumPy. So I'm going to say import NumPy as NP. And so NumPy has, or some people call it NumPy. You call whatever you want. I'm not going to judge you. You're not going to judge me. We're going to unjudge each other. I like to say NumPy. It sounds fun. And then so if you want to use any mathematical functions, they're in this library. They're in this module, so I got to call that. I couldn't even do square root if you don't do that. So just as an example, if I put, I ran that module, so import it, which is kind of slow. So let's say print square root of 2. And then I'm going to run that. It's going to give me an error because it's like, I don't know how to do that. But if I go up here and just say np.square root, it does know how to do that. Okay, so that's just if you haven't used Python before, that's cool. So let's go ahead and enter all our values. I had, let's enter the masses. I had M1 equals 0.15, M2 is 0.15, and M3 is 0.15. And we can change these later, it's not a big deal. Now I need my values of K. I had K1 is 10, not 10 minus. K2 was 5, K3 was 5, and K4 was 10. And you'll notice that my K matrix only depended on M1, M2, K1, K2, K3, K4. So that's all that I need. We can make a matrix in Python. I'll make a simple matrix. A is a matrix. We're going to use an array of arrays. So I'm going to say np.array. Array is a really nice element type in NumPy that allows you to have essentially a list and then just use it as a single variable, which is really kind of cool. If I want to do a 2 by 2, it's going to be an array of, say, 1, 2, 3, 4. So I have a list. It looks like a list of lists. And I didn't put equal, though. And let's print that just so you can see what it looks like. And that's not my matrix. Print A. And there it is. So it lists it as in that form, but it worked. Now let's make the K, capital K. It's going to be np.array. Now here we're going to get a 3 by 3. So I'm going to say the first element. Now I'm going to look at my equation over here. I have K1 plus K2 over M1. So I'm going to put K1 plus K2 divided by M1. No, M1. The next element is negative K2 over M1. And the final element is 0. Now the next row, I need to put a comma and then put another square bracket right there. Negative K2 over M2. K2 plus K3 over M2. Negative K3 divided by M2. And then my last row is going to be equal to 0, negative K3 over M3, and then K3 plus K4 divided by M3. That's that. And let's print it to make sure it works. It should be a number, right? Let's print like this. K equals. It should be a number because all those are numerical values. And I don't want to print A. I just want to get rid of that. And I made an error. See, I knew that. Okay, so it takes K1, K2. I missed a parenthesis somewhere. Array takes 1 to 2 positional arguments, but 3 were given. Well, here, let's see. I just have a typo. Fortunately, I have it up here. Let's just see what's the difference between these two is. No, that was for the 2 by 2. I got to be missing M3. Okay, so there's my start, end. Okay, ooh, That's fine. K2 is... Well, let's just try this. I mean, you can do 3 by 3, right? So put 3... Oops. 1. Oh, I see where it is. I see my error already. See, that's your rubber. I need another square bracket right there. No? Oh, I need another one over here. Got it. Okay. So there is my matrix, my 3 by 3 matrix. Awesome. Now we're going to find the eigenvalues and the eigenvectors. So remember, in this problem, the eigenvalues are omega squared, and I really want omega. So let's find omega squared. I'm going to call it W. Can you see this? Yeah. W squared, because just for fun, and A. And so I want to find both of those at the same time, right? So I get 2 things from the eigenvalue problem. And I'm going to just call np.linearalgebra dot eigenvalue of k. That's it. So I'm going to assign those 2 things to W squared and omega, and I'm going to print them out. So let's print W omega is going to be equal to np dot square root of omega squared, because I want omega. And then let's print A, which is a matrix. Let's see what happens. Here we go. Okay, so here are my 2 angular velocities, which seem kind of high, but I'm fine with that because they're huge. And this is my matrix of values where the answers are column vectors, right? So this first 4 times 10 to the negative 1, 8 times 10 to the negative 1, 4 times 10 to the negative 1. That's my first A1, A2, A3. So let's go ahead and try that one out. And then my second one, my third one. So let's put this. Now, that's 0.4, which is too big, right? That's too large of a starting amplitude. And that's why I'm gonna multiply it by the value of S, because these are normalized eigenvectors, so they have a magnitude of 1, and I don't want 1. It's too big. Okay, so that's going to be x1, x2, x3. So let's copy that, go back over here. x1 is, I'm going to say s times that, and then this one is also s times that. And then actually, this one, no, that's fine. And then this one's that. So s is s times that. Okay, let's see if this runs. Is that a normal mode? And the answer is yes, it is a normal mode, right? They don't have the same amplitude, but they have the same frequency, and you can see it right there. So that's pretty cool. Normal mode number 1. It's kind of fun just to watch. Okay, next one. Normal mode number 2 is going to be this for x1, and then negative that for x3. So this, and then this, but then I'm going to put negative. And then the middle value is 10 to the negative 16th. Sometimes we like to call that 0. So let's just say 0. And so here we have the middle mass is just stationary, and the 2 masses are going like this, and that makes sense. Okay, so that's normal mode number 2. And we can check down here. Yes, they have the same frequency, right? This middle mass has the same frequency. It just has an amplitude of 0. Is that okay? That's true. It's true. That's what it is. Now the last one, we have this 5. They're all the same, but the middle one's negative. Yeah. So this, oops. So the middle one's negative. that negative, and then that not negative. Okay, again, they're out of phase, but they have the same frequency. Same frequency. Okay, now, I mean, what if I want to change one of the masses? What if I want to make one of the masses smaller for some amount? I can do that, right? So if I go over here and I change, let's say M1 is now a little bit smaller. It's not going to be a normal mode. See, they're not normal modes. But if I go back up here and I change that mass in my code to this, to 0.1, I rerun that cell, and I get that K, I rerun this cell, and I got this K, and let's just switch back over here to this last mode. I have this, they're not all the same now, 0.71 for X. Negative 0.35, whatever that is. Negative. And then 9. And now I run it. Normal mode again. Okay. And you can see right there. That is a normal mode. Look at the peaks, they're all lined up. 3 masses. 3 masses, normal modes. It's kind of fun. But definitely, if you want to do this by hand, even for a simple situation, you're going to have to do that. Determinant of a 3x3 matrix and solve for 3 eigenvalues. Please no, I'm not going to do that. But it's still fun to model this stuff. So link to the 2x2 coupled oscillations, which I do by hand and with Python. Also a link to this code if you want to play around with your own normal modes. The end.